Section 4.5 talks a little bit more about solutions now that we know about concentration. And in this chapter, or this part of the chapter, I should say, we're going to talk more about solubility, whether or not things will dissolve or whether or not there'll be a solid precipitate in that solution. Well, we have to define some things first because there's a couple of things that are kind of confounded with each other. And one is the difference between to dissolve and to dissociate. Now, to dissolve means that the molecules or units become separate from the other solid units and it becomes surrounded by solvent, which in our case is always really going to be referring to water in this class for the most part. To dissociate means to actually break apart into ions. So the positive ions come apart from the negative ions while they are dissolved in the solvent. For ionic substances, if they dissolve, they're both going to happen at the same time. They'll both dissolve and dissociate. For covalent molecular compounds, you have some that dissolve and some that don't, but the ones that do dissolve, dissociation doesn't really occur. So how do things dissolve and dissociate? How do these ionic substances do this? Well, there's intermolecular forces between one atom and the next, intramolecular forces actually, that are holding the ions to each other. Those are solute-solute interactions. So the positive ions attracted to the negative ions. Now water, though, which is being represented by these little green spheres, is actually what's called polar, meaning with the shape of the water molecule being what it is, the hydrogens will be slightly positive and the oxygens will be slightly negative. So because of this, it has a partly negative and a partly positive side. So it can get in there and surround the positive ions with the negative side of water and kind of pull it away, because you can have more pull from a bunch of water molecules than you might have from a couple of negative ions surrounding them. And the same thing can happen with the other side. The negative ions can be drawn away by being surrounded by positive portions of water molecules. So kind of how does this look like? Let's look at sodium chloride as an example. Sodium wants to be attracted to chloride, and that's a solute-solute interaction. But the solvent-solute interaction between the negative side of water and the positive of sodium can draw it away. And the negative part, the positive part right here of the water is attracting the chloride ions and can pull them away from the sodium. Now the main key here is on whether or not something will dissolve or not is whether or not you can get enough water to surround the ion to overcome this interaction between the positive and the negative ions. So as a general kind of rule, the more positive and more negative the ions are, the less likely you are to be able to get them to dissolve. So what does it look like in solution? Well, here we have this solid chunk of something like sodium chloride in the center, and the waters are surrounding the little bits on the outside edge and drawing them away. And once it does succeed in drawing them away, it surrounds each ion with a large network of water molecules, which compensate for the fact that it's not around a fully negatively charged ion or a fully positively charged ion anymore. So this is the dissolution, the complete dissolving and dissociating that happens with ionic substances. They are breaking apart and breaking apart into ions. Now covalent compounds don't do this. Instead, covalent compounds, if they're going to dissolve in water, must be doing so because they have some partially negative and partially positive portions themselves. And those partially negative and positive interactions can interact with the water molecules. So they interact with each other, but they can also interact with a water molecule and possibly be drawn away from the other covalent molecules that they were originally attached with. So sugar and water, for instance, is a good example of this. Sugar is a molecular compound, sucrose here in this particular example, and water molecules can get around the positive and negative parts and draw one sugar molecule away from the others. So in a solution, you get the sugar molecules will completely dissolve meaning that the sugar molecule is not next to another sugar molecule anymore. Instead, it's surrounded by waters, and that means it's dissolved, but no ions have broken away. No positive or negative charges have come loose from this structure, so it has not dissociated into ions. Dissolved, but not dissociated. Well, we have a concept also of electrolyte, meaning able to conduct current. Things that break apart into ions and positive and negative charge actually are conducive towards, that was weird, are actually conducive towards allowing electricity to flow from one side of a piece of metal to another. If things dissolve but don't dissociate into ions, they do not help charge move through a solution. And therefore, if you hook kind of a light bulb up to a battery, stick two electrodes into a solution, if you can conduct electricity because it is an electrolyte solution, meaning you have ions present in that solution, then you will get conductance and the light bulb turns on. If you don't have an electrolyte solution, it means that you may have dissolved your substance, but it is not broken apart into ions, and therefore you will not get electricity to be conducted from the battery around, and the light bulb won't light. So electrolyte and non-electrolyte just really deal with whether it breaks apart into ions or it doesn't. Well, we can also have weak electrolytes. So something that is a non-electrolyte, you won't get a light bulb to shine. If it's a strong electrolyte, you'll get a nice bright shining light bulb when you hook this up through the battery. But if you have a weak electrolyte, that means that it dissolves, and a few of them might actually dissociate as well. Not all of them, but just a small fraction will dissociate into ions. So you can conduct electricity, but not very well. So strong versus weak. What are the strong ones? Well, the strong acids and bases. And you want to memorize these 5 acids as being strong acids: hydrochloric, bromic, iodic, nitric acid, sulfuric acid, and the bases are any of the group 1 hydroxides. So sodium hydroxide, wow, great writing. Sodium hydroxide, lithium hydroxide, potassium hydroxide, etc. All those ones in group 1 as hydroxides. Also, any salts that dissolve really well and will dissociate really well, and you'll get a strong electrolyte. Any salts that dissolve. So salts meaning ionic substances. If the ionic substance dissolves, it will also dissociate. Now, weak acids and bases, meaning ones that are not on this list, and I should actually add one more here for you to memorize. Ammonium hydroxide is also, is this strong? No, scratch that. We're going to put that on the weak base side. So I'll leave that with these ones to memorize. Weak acids and bases, meaning they're not part of this list, only dissociate a little bit. So things like acetic acid is a weak acid. Let's see, hypochlorous acid is a weak acid. Nitrous acid is a relatively weak acid. So basically anything outside of this group, not 100% inclusive here, but for the most part, anything outside that group will be a weak acid or base. Slightly soluble salts mean they dissolve, but they only dissolve a little bit. You're still going to see a lot of powder at the bottom of the beaker that hasn't dissolved. And if that's the case, you're only getting a few ions to dissociate, so that will be a weak electrolyte. Now, if the salt just doesn't dissolve at all, like that copper that we had just lumped in there at the bottom once we had the solid copper again, or if you toss some pennies into a beaker, those pennies won't dissolve if they're just in water. So if you have an insoluble substance that doesn't dissolve, it also won't dissociate. Also, if you have covalent compounds that don't have any ionic properties to them, they may dissolve, but they won't dissociate, so you won't get any electrolyte type activity. So, okay, well that's great, but you just said something about salts dissolving. So how do I know which ones do and which ones don't? Well, we have rules, and you'll have to memorize these. It's not too bad. Put them on note cards. Each category on note cards works pretty well. But you can talk about some general rules, such as if there's lithium, sodium, potassium, or ammonium in a compound, then that compound dissolves and dissociates very well. No exceptions to this. If I have nitrate or acetate as an anion, then I also am going to run into a situation where everything that's associated with this will dissolve. Now, chlorines, bromines, iodines, these will almost always dissociate, but if you mix them with silver, lead, or mercury in these as the anion, then you won't get dissociation. They will be insoluble. Alright, so sulfates, that sort of thing. You get the idea here, right? There's some rules that tells you if it's soluble or insoluble. So let's try it. Sodium chloride, I checked the list. Sodium, always soluble, so this one, definitely soluble. That will be a strong electrolyte. That is the worst rating of soluble ever. There we go. Sodium carbonate. Well, carbonate, usually not soluble. All these are generally not soluble on this side. But if I mix it with sodium, it is. So, soluble. Lead acetate. Lead tends to be insoluble. Evidently they're vacuuming out there. Lead tends to be soluble, but acetates, if we look up where the acetates are, here, then acetates are generally always soluble, with no exceptions. So this is soluble as well. How about lead chloride? Okay, well, chlorides are soluble, but not with lead. So non-soluble or insoluble, which also means it will be a non-electrolyte. Sodium sulfide. Well, sulfides tend to not be soluble, but when you mix them with sodium, yes, soluble. Calcium sulfide. Well, sulfides are generally insoluble. When sulfide pairs with calcium, strontium, or barium, the resulting compound is soluble, so that one's soluble too. Excellent. Oh, beautiful. How about one more? How about magnesium sulfide? Okay, so sulfides are insoluble, except with calcium, strontium. Magnesium's not on the exception list, so insoluble. Excellent. So those are the rules. That's how we figure it out. Voila.